Hello friends, welcome to another problem from Graduate Math Solved. This one is a pretty difficult problem. I gave it a 4 out of 5 chili peppers because of its tricky nature. This did end up on a qualifying exam at the University of Pittsburgh in some year. And I am going to solve this problem right now. But first, let's see what it says. For P and Q in R2, a pair of real numbers, we associate a polynomial fpq is x cubed minus px plus q. Prove that for any y and z in R2 that you fix, there exists a unique pair pq such that y and z are roots of fpq. And we understand that if y equals z, this means that it is a repeated root. In part 2, we want to show that this association, this map from YZ to PQ is at most 6:1. There could be 6 different YZs that map to the same PQ, but not more. And in part 3, we want to show that if this is the case, if PQ is one of the cases where you have a 6:1 map, then in a neighborhood, you have a local diffeomorphism. Okay, so let's see where to start. But before that, I want to show you the situation in 1D and in 2D. So here is a picture of a cubic map. So something like this, right? Because x cubed has +1 coefficient, it goes up in this end. So this is the polynomial, suppose, associated to a particular P and Q. And here are the roots y1, y2, and y3. The map that we're talking about here is y1 and y2 will be mapped by this phi to this P and Q. And what other points can you find that map there? I can find y1 and y3. These again map to the same PQ under phi. But then also I have y2 and y3, and I have now 3 points, but also y2 and y1 is a different point because these are distinct, and so on. Well, maybe there's one left. Let's write that down too. So, and then there is y3, y1, and then y3, y2. So 1, 2, 3, 4, 5, 6 points, all mapping to the same P and Q. So here, the same PQ polynomial has 3 distinct roots at the maximum possible for a cubic. And in this case, you have 6:1. So could there be different number of points as well? So this actually proves part 2 that the map will be at most 6:1 because you cannot have more than 3 distinct points. We can get fewer. For instance, when you have this one, suppose this is a different P and Q, giving a different cubic, and then now you have 1 and 2 distinct roots, but one is repeated. So if this is y1 and y2, then I have y1 and y2 mapping to PQ. I have y2 and y1, just different order. And then I have y2 and y2 again because it is a repeated root. So the pre-images become 3. Can I go lower? Actually, I can. For some P and Q, which you can guess, for instance, if you choose P equal 0 and Q some positive, you can have such a polynomial. And there are no YZ actually maps to this PQ. So this is showing that the map phi is not actually surjective onto R2. Some P and Q just do not produce 2 roots. So these are the types of things that happen. This is how P and Q and pairs are associated. But for the problem, we actually are dealing with a two-dimensional problem. So here's one copy of R2, and here is another copy of R2, and then you have points YZ, which map to point P and Q. And we are saying in part 3 that if this PQ is one of those cases where I have 6 distinct points, then around each one of these YZs, there is a neighborhood on which phi becomes a diffeomorphism. Of course, it has to be onto an open neighborhood of PQ. So part 3 is claiming that locally this phi becomes diffeomorphism under the assumption that I have 6 preimages. And we saw above that this happens only when no repeated roots occur for PQ. Repeated roots of FPQ. So all these observations just help us understand the situation and what is going on. And with that, we are ready to actually prove the diffeomorphism part of it. Forgive me if I haven't written down anything for part 1 and 2, because I think I gave enough details so you can fill that out actually on your own. So part 3, I want to show that phi is a diffeomorphism. And for that, I need to know a couple things for my P and Q. Number one, I need to know, so I want to apply inverse function theorem ultimately. And for that, I need to know that phi is a smooth map. And number 2, that its derivative is not 0. If I have these two, then inverse function theorem says that phi itself is a diffeomorphism locally. So I need to know that phi is smooth, and I need to know that derivative of phi has full rank. Its determinant is not 0. Then apply inverse function theorem, which guarantees that there is an inverse, and that inverse is also smooth, which is exactly what diffeomorphisms are. But let's see if we can show these. So how do P and Q depend on Y and Z exactly? And also this, by the way, is a proof of part 1 as well. Suppose Y and Z are roots of FPQ. Then FPQ of X can be factored out into X minus Y, X minus Z, and then a linear part, which is A X minus C for some A and C. However, because this guy has X cubed in it, 1, coefficient of X cubed is 1, this means that A can be nothing other than 1. So this has to be 1. And so I go ahead and actually simply remove it. So what I get then becomes that there is X minus C here. And you multiply this out, and compare the coefficients. So if you compare the coefficients, we see that coefficient of X squared has to be 0. This will imply that C has to be equal to Y plus Z. And once you replace C with Y plus C, you also get that P and Q have polynomial formulas. You can precisely compute these formulas by just doing the computation above in terms of y, and z. So in particular, this phi, which is a function given by yz and q of yz, that's how it's defined, is C infinity. Okay, it's polynomial, so it's C infinity. The reason I'm not actually giving you the formulas for P and Q, although I have them in front of me, is that interestingly, the explicit formulas for P and Q that we find are not useful in proving the second part that the derivative has full rank. Also, this computation that I just did can be reversed. So if you give me y and z, then I set my c to be y plus z, and I set my p and q according to the formulas, and then I can work backwards. So I start with y and z, I define p and q via those formulas, then it shows that this can be factored down, and then it shows that if pq has these roots, in particular, it has roots y and z. So it works both ways, which is a proof of part one. And P and Q have no free variables in them. So they are uniquely settled by y and z. Now let's go to the main part and the last part, which is showing that the derivative of phi has full rank. So again, the explicit formulas, interestingly, aren't helpful here. What is helpful is the following. I know that y is a root. So this y cubed minus py plus q equals 0. And z is also a root. pz plus q is 0. So these implicitly give p and q as functions of y and z. So let's take implicit derivative. So taking derivative with respect to y and derivative with respect to z in both equations and on every side of every equation gives the following formulas, which I have computed and simplified for you. What you get is that 3y squared minus partial of p partial y multiplied by y minus p plus partial q partial y is 0. There's some product rule there and chain rule, but it all is coming from the reason that we are doing implicit differentiation. So negative z partial y plus partial q partial y is 0. So this was just taking partial with respect to y of these equations. Z and y are independent from one another, keep that in mind. Now, when you take partial with respect to z, you get this one. So negative y partial p partial z plus partial q partial z equals 0. There is some confusing symmetries here, but I just want to ignore them because they make my head spin. Partial p partial z minus p plus partial q partial z is 0. So you get these four equations. And what do they have to do with the derivative of phi? Well, derivative of phi, remember, is partial p partial y, partial p partial z, partial q partial y, and partial q partial z, right? So the goal is to show that this matrix is invertible. Or I can for the reasons that will be apparent soon, I want to actually look at the conjugate, I mean the transpose of this function. So I want to put Q here and P here. So I want to show this matrix is invertible. If you summarize this and this, there are 4 equations here. If you summarize into matrix notation, something magical happens, and I found it by simply trial and error. So you multiply by -1 and -1, then this becomes the following. You get 3y squared minus p, 0, 0, 3z squared minus p. Okay, now we know that y is not equal to z. It's not a repeated root, right? This is one of the points where you had 6 preimages. From that, we see that this matrix is invertible because its determinant is simply z minus y, and that's not 0. Okay, that's the proof. And on the other hand, look at so if something is not a repeated root, then that means it's not a root of the derivative of the function. So if y is not a repeated root of f pq, that means f prime pq of y is not 0. And similarly, f prime pq of z is not 0. That is not a repeated root either. From this, you get that what is derivative of f pq? It's 3x cubed. So I want to replace y. 3y cubed minus p. That's exactly the derivative of f prime evaluated at y. And similarly, 3z squared minus p is not 0 either. From this, you get that this matrix is invertible because none of those diagonal terms is 0. And done. You have invertible, and if you multiply from right by the inverse of this matrix here, you end up this equal to an invertible matrix. So the conclusion is that this is invertible, and that's exactly what was needed for the inverse function theorem to apply. As I said in the beginning, this is not an easy problem. You'll probably want to download the PDF that I put in the description of the video and go over it on your own to see the intricacies of the problem. The reason I think this problem is really difficult is because you have the explicit computation for P and Q, but they are not helping you. And it's very difficult to know on an exam beforehand that some path this promising will not lead to a solution. And that's why I think it's kind of a confusing problem. So hope to see you in another video. Please subscribe and support our channel and spread the word to friends.